Okay, let's have a look at the question. It's a standard level question. It would work for AA or AI. As we read through it, I'm going to highlight keywords. The time it takes Susie to drive home from work each morning is normally distributed. Normal distribution. Mean of 35, standard deviation of sigma. Okay, so let's go ahead and let T equal the time to drive home. T can be modelled by a normal distribution with a mean of 35, a standard deviation of sigma. Okay then. So now on 25% of these days, it takes Susie longer than 40 minutes. So the best way to tackle these questions is with a nice diagram. So for part A, let's go ahead and get an x-axis with T. Let's get a nice normal distribution. Sigma, we don't know. The mean is 35. And the question says, on 25% of days, it takes Susie longer than 40. So let's go and put 40 on the diagram. And let's put 25% on the diagram, right? Okay, so it looks like we've got a probability, we've got a mean, we've got the number, but we don't have sigma. So this is a clear sign that we will need that magic formula, z equals x minus mu over sigma, which is the standardized normal distribution. Now I'm going to put a little z-axis here. And what we can do is, we can say on our standardized normal distribution, if I want to be standing somewhere on a normal distribution so that 75% of the data is to the left of me, where would I be standing? How many standard deviations would I be above the mean? So here we're just going to switch to our calculator. And we are going to go menu, probability, distribution, and we're going to go ahead and do an inverse normal. Oh, I think it was right at the top, wasn't it? Inverse normal. The area is 0.75, so we always have it from the left up to where we want, and the standardized normal means 0, standard deviation of 1, click. Oh, let's go back again. Looks like I had a little bit of an error there. Menu, probability, distribution, inverse normal. Okay, so the area is 0.75, and go ahead. So 0.674. So we are standing at 0.764 standard deviations above the mean. Is that right? 0.674. Ooh, that would have been a mistake. 674. Okay, so basically standing at 40 means that I'm exactly 0.674 standard deviations above the mean of 35. Now if you can't quite get your head around that, just go ahead and use the formula. Okay, so the z value was 0.674. The x value is the 40. The mean is 35. And the standard deviation is here. So we eventually get just to this calculation. Right, then we can go and solve for sigma. So 5, let's go in here, 5 divided by, we can use the full accuracy of the answer, and we've got 7.41. So sigma equals 7.41, and I think it was minutes was the units, right? So back to here, we now know that sigma equals 7.41 minutes. On a randomly selected day, find the probability that Susie's drive to work will take longer than 45 minutes. Okay, so now we've got the standard deviation. We can just go ahead and draw another picture. Okay. So we had the previous question was 7.4, yep, okay, great. So here's part B, and we'll put on 35 again. Sigma here now is 7.41, and the question asks us longer than 45 minutes. So we want the probability of t being greater than 45. It's always nice to give a mathematical description of the question. So let's go ahead and get my TI Inspire out again. So we're going to want a particular area, so menu, probability, distribution, normal cumulative distribution function, CDF. Lower bound 45, upper bound, you can put in a big number. As long as you're more than 5 or 6 standard deviations above the mean, it doesn't really matter how big the number is. And the mean is 35, and the standard deviation is 7.41. So 0.0, let's put that side by side. There we go. 0.0886, that's 3 sig fig, right? Okay, let's go again now. Susie will be late to work if it takes her longer than 45 minutes. Okay, the time it takes to drive to work each day is independent of any other day. Okay, Susie will work 5 days next week. So this is where we've transitioned from, we've got a probability of taking longer than 45 minutes for this section, and now there seems to be a repeated driving to work, and we kind of say that n equals 5, and we've got a probability here that we calculated from before, which was 0.0886, 0.0886. Can you see this looks very much like a binomial, right? It's got a fixed number of trials and a probability of success. So I'm going to put let x equal the number of times late. So x can be modeled by a binomial. 5 is the number of trials. 0.0886 is a probability of success in this case, is being late. Find the probability you should be late to work on at least 1 day. So the probability of x is greater than or equal to 1. All right then, so we found it. Back to the calculator. Menu, probability, distributions, binomial CDF. Number of trials is 5. Success 0.0886. Lower bound is 1. And upper bound is 5. 0.371. So it's equal to 0.371. Cool. Now then, given that, so there seems to be a conditional probability happening at the end here, given that Susie will be late to work at least 1 day next week. Okay then, so here's where I'm going to draw a little table of values, because this table of values actually helps me. So here is my table of values for x. 0, 1, 2, 3, 4, 5. Okay, don't need that there. Now for each of those, there's obviously probabilities attached. Okay. Now what we're doing is, given that Susie, oops, let's just go and undo all that. Given that Susie will be late to work on at least 1 day next week, so we're choosing from these probabilities. Find the probability that she'll be late less than 3 times. So you can see the sneaky question now. So from those blue probabilities, so it's actually conditional, so we're going to have a denominator, and from those probabilities, which we've already found is 0.371, which particular sections do we want? Find the probability she'll be late less than 3 times. So that would be 2 times and 1 time. So here we want the probability of x equaling 1 plus x equals 2. So that's a bit sneaky, that conditional probability. But look, you can see it's going to be a tough one because it's a 5 marker, right? So it's a 5 marker, so we've got to be, thinking quite a lot for this one. So let's go ahead on our calculator. We'll go get that numerator first. So it's, oh look, I can go up. Oh no, let's just do it again, I think, because we've got, we can do, let's go up, because we've used this already, up, binomial CDF 5, yes, 0.8666, but in here I'm going to edit it to do 1 and 2. So that's 0.365, so let's go ahead and transfer that to the question, 0.365 0.365, and that's divided by 0.371. Okay, so divided by 0.371, it's a very high probability, so that's approximately 0.984. Oof. Okay, nearly there now. Last piece now. I'll just get some of these out of the way, right? Okay, right, then let's have a clean start for the end. Susie will work 22 days this month. She will receive a bonus if she's on time for at least 20, so she needs 20, 21, 22. So far this month she has worked 16 days, so therefore she's got 6 days left to work. And she's been on time for 15. Ooh, right, okay, so 15, so she needs to get to 20. So from the 6 days that she's got left to work, she has to be on time in 5 or 6. Okay, so there's 6 days left to work. The probability that she's on time, well, I think we had that from before, right? Wasn't it 0.0? Oh, there we look. This was the probability of being late, 0.0886. So the probability of on time is 1 minus 0.0886. So should we go y is a binomial, 6 here, and the probability of success, let's see if I put it in my calculator, 1 minus, okay, being on time is 0.91, 0.9. 0.911 I got. Okay, so we want the probability of y being greater than equal to 5. That'll be a binomial CDF. Let's go ahead and do that. Menu, probability, distributions, binomial CDF. Number of trials is 6 days left to work, right? Success is being on time, 911. Lower bound is 5, upper bound is 6. And there we go. So that is 0.907. Okay.